A pressure outlet boundary is a flow outlet boundary at which the pressure is specified. It is used in conditions like specifying outflow of compressible and internal flows. An example can be a plenum in which boundaries surrounding a jet emanating into a large chamber. A pressure outlet boundary cannot exist in the same continuum as a flow split outlet. Although *CCM+ does not prevent a pressure outlet boundary from being used as an inlet, a stagnation boundary is a better choice in such cases. The stagnation inlet boundary is an inlet condition that is well pushed for compressible flows, although it is equally valid for incompressible flows. The stagnation conditions refer to the conditions in an imaginary plenum far upstream in which the flow is completely at rest. For incompressible flows, Bernoulli's equation is used to relate total pressure, static pressure, and velocity magnitude. For compressible ideal gas flows, isentropic relations are used. In this case, the characteristic variables determine the propagation properties of the flow. In compressible flow, the total pressure, total temperature, and flow direction are always used to obtain the inlet flow conditions. Confusion often arises, however, about the need to specify the static pressure at the inlet, termed supersonic static pressure in *CCM+. The characteristics of the flow dictate that when the inlet flow is supersonic, all information comes from upstream conditions, including static pressure. This flow regime is termed hyperbolic, and the situation dictates that supersonic static pressure must be appropriately specified. When the inlet flow is subsonic, the flow regime is termed elliptic, which means that the static pressure is obtained from the downstream flow. In this case, the value that is specified for supersonic static pressure is ignored, and ideally, its value could be left at the default. This is not always advisable, as in some situations, the inlet flow can momentarily become supersonic during the simulation iteration. If this occurs and the supersonic static pressure is improperly specified, the solution might diverge. In these situations, it is recommended that isentropic relations be used to specify a value for supersonic static pressure that corresponds to a slightly supersonic match number. It is applicable in case of the inlet to a simulation of internal flows for which the stagnation conditions are known. It should be used in combination with pressure outlet boundaries. A stagnation boundary cannot exist in the same continuum as a flow split outlet boundary. A symmetry plane boundary represents an imaginary plane of symmetry in the simulation. The solution that is obtained with a symmetry plane boundary is identical to the solution that would be obtained by mirroring the mesh. This mirror is about the symmetry plane in half the resulting domain. It is used as an imaginary plane of symmetry in a simulation that would be physically symmetrical if modeled in its entirety. A velocity inlet boundary represents the inlet of a duct at which the flow velocity is known. It is used as an inlet to a simulation of incompressible internal flows. It can be used in combination with pressure outlet and flow split outlet boundaries. It should not be used for compressible flow, as this boundary does not prescribe the total energy of the system, which is important for compressible flow. *CCM+ does not, however, prevent the use of velocity inlet boundaries for compressible flows. Next is wall type. A wall boundary represents an impermeable surface. It is used as an impenetrable boundary for inviscid flows. It also acts as an impenetrable no-slip boundary for viscous flow simulations. It can be used as slip faults representing an impenetrable but traction-free surface. It is also applicable as boundary of a thermally active solid region at which the temperature or heat flux is specified. When a new interface is successfully intersected, new boundaries are created. These appear in the simulation tree and have types that are associated with them defined by the type of the interface. These boundary types cannot be changed except by changing the interface type. The possible generated boundary types are baffle boundary, contact interface boundary, fan interface boundary, fully developed interface boundary, internal interface boundary, mixing plane inflow boundary, mixing plane outflow boundary, and porous baffle boundary. The name of the interface boundary cannot be changed except by changing the names of the original boundary and the interface.